Welcome back to DeepRob for lecture 11. In today's lecture, we'll talk about some popular deep learning software frameworks, and these are things that on a practical level, you have some experience now going through the projects that we've been through, but moving forward, both in the course and then beyond the course, you'll certainly be relying on, in all likelihood, these frameworks that we'll be talking about today for your future deep learning implementations. Before we get into PyTorch, TensorFlow, and some of these frameworks, I do want to make a couple of administrative updates. So the first one is on Project 2. I decided to move the deadline for Project 2 by like a full 48 hours. This is because I was so slow in getting the autograder up, I just felt like this maybe will help just give like a little bit of extra time to everybody. So I won't also release the project code for the next project, Project 3, until this one is due. So it also gives myself a little bit of extra time for that. Let me think. So the other thing on Project 2, I guess the other like administrative update. So that I'll just point out, I've updated the website with that due date. I still have to update it in the autograder, but by after like maybe an hour after lecture, the autograder will say that the due date is changed too. But if you already have it done, there's no need to worry. It's just like if you want extra time, now everybody has a bit of extra time. Okay, on the final project, so a couple updates on the final project. So just as like a brief reminder, the goal of this final project is to give you some experience like on the research end of deep learning and robot perception. So this is going to take the place of any final exam that we might otherwise have had. And on the project website, like we have now some actual instructions, but a big update, which hopefully everybody has seen, is that you should have gotten an email from me I guess depending on your definitions of late, pretty late last night, that should have shared your project teams and also the paper that your team has been assigned for the review and presentation portion of the final project. If you didn't get an email from me, I think it's because you didn't fill out the survey. So come and see me if you didn't get that email, and we can find like a paper assignment and maybe a team for you if you want to work on a team. So on the project on the course website under the project section, we now have, like as of a few days ago, this final project page, which is still getting updated, but for the review portion of the final project and the presentation portion of the final project, we now do have instructions there and some templates that you can use. So for the review, we have a LaTeX template that you can use for your review. For the presentation, we have both a Keynote template or a Keynote theme and a PowerPoint template, which are just basically like the shell of this slide format. So we ask that you use those two templates for the review and the presentation. In terms of the due dates for these two portions of the deliverables, what we are asking for each of the teams is if you could submit your paper review 1 week before your presentation. I'm thinking that for both of these, the submission should just be via email to me. I've thought about Gradescope, but I think Gradescope makes it a little bit hard to kind of download the slides as a PDF on my end. So then for my purposes, like formatting it into one slide deck is a challenge. So just send them to me by email, and I'll put that on the course website. So 1 week before your presentation is when we ask for the review to be done, and then 3 days before the actual lecture when you're scheduled to give the presentation is when we ask that your slides be sent to me. And the reasoning behind those two, those two kind of due dates is doing the review before the presentation will ensure that you've actually sort of gone through the paper and you've read the paper and you do have an understanding of it before you actually would have slides, as opposed to having the two due dates be consecutive, because I think it's better that you actually start thinking about these papers before you think about how you would present them to others, because you really need an understanding of the material before you want to go and share the concepts with others. Within that, though, I do realize that like for the first groups, so like the 3D perception project or papers, these due dates are now like within 3 days roughly, because like starting on Monday would be 1 week from the start of those lectures. So I think the trade-off that sounds reasonable on my end is like in general, I'll be like flexible with these due dates. I'm not gonna like mark anyone like as like fail, like it's like a 0% if you're late, or like 50% off if you're late by 1 day. but don't abuse it at the same time. So for those first groups, I can be very flexible because I do want you to have enough time to actually structure a nice review and do a nice presentation. So I would say for those first groups, if you could get and you should know who you are if you're in the 3D perception category, but if you could give me both of these by like the Friday before, which would I think be a week from tomorrow, that would be nice, just so that I have enough time to structure the slides and things. Question? Yeah, so the paper review and presentation should be as a group. So yes, you can work collaboratively on both. So on both. I would strongly encourage you all to maybe like on the review side to maybe all like try drafting a review by yourselves and then come together and talk about what you all think. I would if you guys really want to, you could sort of like divvy up the work and say, you do the review and I'll do the presentation. I wouldn't recommend doing that though, because I think the purpose of this project really is it's for your benefit to go through these things, because on the research side, this is what if you are a grad student currently, or if you plan to be a grad student, or if you're doing research, whether undergrad or grad, doing paper reviews, giving presentations are two of the most important parts of being in academia in those roles. So it's a good experience to go through. And I know that, I do realize also that this final project is sort of, it's not as clearly structured as these other projects, right? So there's not an autograder, and these due dates are different for all these different groups. So I think that's in part good, because that means that we're gonna have a lot of diversity in these final projects, and we're gonna cover a lot of material. But I also realize that from a scheduling standpoint and just planning out your week to weeks, it's also adding some uncertainty and some challenge. So it does that on our end too. So like I said, we'll be as flexible and reasonable as we can on our end, but we would just ask that with the due dates and things like that, that you try and stay on top of your kind of work and your responsibilities. Any other questions I can answer about the team assignments or the review, the presentation portion? Yeah, another question? Yeah, so let me show you. So the question was, how can we find what day our presentation will be on based on the calendar for the course? So let me pull up the course website. So if you go to, so there's sort of two ways you can do this. So the first way, so if you go to the paper page, you can figure out which category in these broad topics your paper falls into. So just as an example, if you do a control F, a find for the paper that you were assigned, so I'm just picking one out of the hat, which is the first one, which is Pose CNN. So if you do a control find for Pose CNN, you'll be able to find which broad category the paper falls into. So Pose CNN is an RGBD architecture paper. So from there, for each of these broad categories, we put a link to try to help a little bit to which specific week and which specific lecture that paper presentation should fall into. So either if you memorize the calendar schedule, or if you just click this link, it'll take you to the actual lecture in which that presentation should happen. So you can see it automatically took us to week 8 and lecture, it's hard to read from my perspective. Is that lecture 14 or 13, something like that? Yeah, lecture 14. And you can do an exact, all of in my email, the title of the papers that I sent should exactly match what's on the paper page. So you should be able to do a find for those exact titles. Does that make sense to everybody? Yeah, okay. Okay, let's see, we have an online question. When we say reproduction of the work, is it meant to make the model work with the data set they've tested on, like a pre-trained one, or is it supposed to be from scratch, training the model ourselves and evaluate how we've done? Okay, so that question is asking in regards to the deliverable number 3 for the final project. So not the review, not the presentation, but on the technical side, once your project or once your team has sort of figured out what paper, which can be a separate one than you're presenting, you guys want to try reproducing, what does a reproduction mean? So from our standpoint, if you can reproduce one of the results from the paper, then that's what what reproduction means. So if the paper that you are interested in for the technical side has no code publicly available, then you would have to re-implement the code to reproduce any of the results. Based on that, we would recommend probably looking for papers that have code publicly available. And in terms then of like what exactly does reproducing mean, it'll now depend on what paper it is you're interested in working on for those final 3 deliverables: the reproduction, the extension, and then the project report. So in the case of, let's say, like in the case of Post CNN, they have code publicly available. So you could download their code base. The data set for that was publicly available. So if you can essentially run their code on their data set and even reproduce either a qualitative result of tracking one of the objects, pose, or a quantitative result of actually establishing like what was the error metrics that they reported for the sugar box, that would also be a valid like reproduction. So it'll depend somewhat on the paper, but hopefully that adds some clarity. I'll plan to talk more about the reproduction, I think, on probably maybe discussion tomorrow or maybe next week, because those ones are still, like those final 3 portions of the final project are still, we still have a few weeks before those are going to kind of come into the full swing. So the question was, for the reproduction part and the algorithmic extension and then the final project report, does the paper that we choose to reproduce and extend, does that need to be the same as what we're presenting and reviewing? So, and then there was a second part, but to that first part, no. So the paper you're reviewing and presenting, that, like the core staff, we assign to you. You can choose then to reproduce and then extend a different paper of your choosing, as long as it's within robot perception and deep learning. So there should be some tie-in to robots and deep learning. And if you're concerned about the tie-in, come and talk to me, so like during office hours or after one of our lectures or discussions. I think and again, like this is the first time we've done this final project, so we're still trying to figure out what makes the most sense. One of the things that I think we're gonna plan to do, if I can find the calendar, is I think it will be helpful to in some way give some feedback about what groups want to do for the final project. So I don't want to have like I want to be reasonable with the time demands of this course, because we do have a lot of implementation-based projects, and this final project I do expect is fairly sizable if you kind of take it seriously. So we have this like proposal item on the calendar if you've looked at it. Right now, I'm planning to kind of throw that away as an actual due, like a portion of the assignment that's due. But having said that, I do want to give feedback to your ideas. So potentially during discussion hour or during office hours, I would strongly encourage groups to come and talk to the core staff. I mean, it can also be Huiji and Jiwei. But because I do think that coming up, especially with the extension side of these projects, that really is where, that is true research. And I think there's so much uncertainty with, as a number of projects have already been talking with me about, it is actually really hard coming up with some of these new ideas. So right now that we don't have a structure like you have to do a one-page proposal and then submit it to us. But I would strongly encourage you to come and talk with us, probably before spring break, just to see where you're thinking, and we can give suggestions on things to consider on that end. Yeah. How are people, are people very stressed about the final project? Are they super excited? I think this is a really exciting final project because we're giving you a lot of freedom. Good, okay. Okay, and I think, so the last thing I'll just mention on the topic of this kind of administrative update is just, I did my best to match everybody with their interests. So I think I got everyone who requested a specific grouping, I'm pretty sure I got all of those exact. And then even within those, I got most people's preferred papers from my, that was itself a non-convex optimization problem last night. So that I think I managed to get most of everyone's grouping or if they want to work as an individual, working as an individual plus their paper. There were a few where I could only get one of the two, so I would, like maybe I got your group exactly how you wanted it, but your paper was like third preference or something like that. But I did my best. So if you have concerns about that, you can come and talk to me, and we can maybe work something out. But okay, so with that, unless there's any more questions about this administrative update, then I think we'll get into the project material. Okay. So as a recap, last lecture, actually the last two lectures, we were talking about how to start training our neural network architectures. So from 2 lectures ago, we saw how like the choice of activation functions, what preprocessing used, the regularization used, all of these hyperparameters can be set up, and that will influence the performance of your model. But then also, once you actually start training the model, in last lecture we talked about these training dynamics and how by scheduling a learning rate decay or doing maybe like a grid search over the hyperparameters like during your development, how all of these things can impact the actual resulting performance of your model in terms of accuracy on some benchmark that you're interested in at test time. But that doesn't actually sort of describe the full story of how it is we go about training these architectures. So in particular, like in kind of like a realistic scenario, you're not going to implement all of your training infrastructure from scratch the way you're doing it on the projects that we've talked about so far. Instead, what you'll do in practice is you'll use one of these deep learning frameworks that have been developed generally in an open source format for you to sort of do a lot of the heavy lifting on the low end. And then you'll just worry about the high-level architecture and those high-level hyperparameter questions. So giving like a broad overview of some of the frameworks that have been developed, what are shown on this slide, I would say, are a collection of some of the more popular frameworks. So, but this is not all of them. There's sort of new frameworks coming up around all the time, and in the past there have been many projects started for supporting deep learning. So like around 2014, one of the very popular ones, one of the sort of early ones was Caffe from UC Berkeley, and then that was sort of like continually developed by Facebook and then turned into what's called Caffe 2. So that was sort of like a C and C++ based implementation. Another one that I think is kind of interesting on the C and C++ side is from Joseph Redmond, Darknet. Just like as a personal anecdote, when I worked at a national lab with deep learning, one of my coworkers would only ever use Darknet. So even if there was like a new architecture proposed and they wanted to re-implement for their projects, they would actually go to C++ and use Darknet to re-implement it, which I just always thought was like fascinating, funny. But then more commonly, the two that we mostly will be seeing and what we've already been working with, for example, are PyTorch and TensorFlow. So these two are certainly the most common and most popular deep learning frameworks. So PyTorch, so that historically has been developed by Facebook. So it's an open source project that came from an earlier project which was called Torch. And TensorFlow, on the other hand, was sort of inspired heavily by a previous open source project called Theano from University of Montreal. But as is kind of indicated on the slide, these are not the only ones. So sometimes there's like a new one from Google called JAX, which is increasingly becoming popular, but it's still not at the levels of PyTorch or TensorFlow. And then sometimes for like specific industry applications, they might rely on like an internal, like some internal preference. So like Microsoft has this CNTK, Amazon, like AWS will use MXNet quite a lot. But generally speaking, PyTorch and TensorFlow are the two that you'll most commonly see. And even within that, I think PyTorch on the academic side tends to have a slight edge, which we'll talk a little bit about today. So today's focus will be on PyTorch and TensorFlow. It's possible I might only have time to go over PyTorch today, which is okay because this course we're sort of building it all in PyTorch, all of our projects, and PyTorch, like I said, is my personal preference. So we might not have time to get to TensorFlow, but if you're interested in TensorFlow, the slides will be left up online. Okay, so there's been a lot of these frameworks developed, and it sounds like they might be useful for something, but then the question is like, what is it really that they'll be useful for? Because so we mentioned like that, doing that like low-level infrastructure on the training side maybe. At the core, what all of these frameworks are going to do is really be handling the computational graphs for our training for us. So if you'll recall from our discussions of doing like backpropagation with neural networks, this idea of a computational graph was a data structure that could be used by the backpropagation algorithm to calculate all of our gradients automatically so that during training, we can sort of construct different computational graphs and not have to worry about how the individual kind of gradients are being calculated on a case-by-case basis. We can sort of generalize the gradient calculations by relying on this data structure. And ultimately, that's what these deep learning frameworks are going to do. So they're going to hopefully set up for us some implementation of a computational graph, and it will be abstracted in a way that will allow us on the higher level side to do very rapid prototyping. So if we have some new architecture idea, hopefully their API is set up very nicely so that we can try that new architecture idea easily and not have to worry about tinkering with the individual gradient calculations. So that's one goal. Another goal then is like, for actually solving the backpropagation, it should solve the backpropagation for us. So those two are kind of intertwined. And then a third goal, which is also something that is important and we've sort of run into in the projects, is it can be nice for, on the development side, to sort of set up a CNN architecture agnostic to the hardware that it's actually going to be run on. Because depending on what stage of development you're in, or if you're maybe going to deploy the architecture at some point, you don't necessarily want to think about the low-level details of what hardware platform your architectures are going to be running on, because that adds a whole nother layer of complexity to the development. So hopefully what these deep learning frameworks can do is they can be built in such a way that on the developer side, we can sort of assume that they'll handle all the hardware optimizations for us so that our networks ultimately can run very efficiently, whether it's a GPU platform, maybe even a CPU platform, or the TPU, which is like a tensor processing unit, which is made specifically for neural network architectures as opposed to the GPU, which is more general purpose for parallel computing. But hopefully the deep learning frameworks can also be set up so that they handle that hardware optimization, at least some of it, for us. And so PyTorch is one example of a deep learning framework that tries to address all of those three motivations, and it's one that we have some familiarity with from the projects, and so we'll talk about it to start with. So for this class, what we've been working with in the projects is a specific version of PyTorch called 1.13. So this was released just in October of last year, and PyTorch, because it's open source, you can actually see all of the release history. You can see how PyTorch has been changed, what their like long-term goals have been. And so with that in mind, one thing that's kind of important to note is like you'll sometimes be like looking at older papers, which might even be from like 3 years ago or 4 years ago, and they're implemented with a different version of one of these deep learning framework APIs. So you might be looking at a paper, for example, that's using PyTorch from before there was actually version 1.0. And so in those cases, the API might look different. So that's just something to be aware of. Another thing to be aware of is that actually very recently PyTorch has announced that they're going to officially have version 2.0. And so we're not going to talk about that in too much detail. I think this actually is like a video, which is kind of funny. So we're not going to talk about PyTorch 2.0 in too much detail because for our projects, we're going to be sticking with 1.13. But it's something to be aware of because I anticipate that once it's stable, which they expect to be in March 2023, version 2.0 will sort of be the standard on Colab and a lot of the projects that you'll see built with PyTorch. From my looking at it, the main difference is that they now support this essentially like more advanced optimization through a function that's called torch.compile. So it's as we'll see coming up, PyTorch 1.10 like has a lot of these optimizations built into it, but 2.0 is just like the next level, like kind of like the next step in having some of these optimizations with regard to the speed of your computing built in. And one thing that's nice about PyTorch 2.0 is that they've been developing it so that it's backwards compatible with all of the 1.0 or 1.13 code. So if you wanted to move your existing models into 2.0, it sounds like there's not issues coming up, broadly speaking. And one thing that's kind of like, so if you're interested, there's a link here. It's like where this video I got it from was from the blog post announcing the version 2.0. And they do a nice job talking about some of the history with PyTorch, their long-term goals, how they feed into those three motivations we saw on the last slide. And there is this general trend that they point out, which is really nicely pointed out in this figure, and it's worth kind of thinking about, is that like because of Moore's law, right, like computation has been getting cheaper and cheaper and cheaper. And in particular, because neural networks have been so successful, there's been like more and more emphasis on making the specific types of hardware platforms that work well with neural networks to be cheaper and cheaper and cheaper because there's so much industry interest in applying neural networks. So what's happened over time is GPU computing, which is what's very useful for speeding up neural networks, has been essentially getting cheaper and more powerful. And as a consequence, what happens, and we saw this in the history of like those CNN architectures, is people try to build more and more complex networks because they can do so with the cheaper compute that they now have access to. And so like there's this constant struggle between, for the API developers, of like people are building more complex networks and they have more compute, but the APIs need to be able to support that higher level of complexity for the model development. So if you're interested in like pure software development, it's an interesting problem to think about. But okay, so back to like PyTorch 1.13. There's a few fundamental concepts baked into PyTorch. And so we've been familiar by now with tensors. So tensor really is kind of like the core data structure. It's probably the lowest level of the API that you'll sort of on like a day-to-day basis be interacting with in PyTorch. And at its core, what the tensor does is it stores data in an array-like structure. So it's similar to a NumPy array. The main difference from a tensor to a NumPy array is that the tensor has been optimized for GPU kernel processing. In addition, though, PyTorch supports a few other kind of core kind of like operations or core like API structures that we haven't actually interacted with so far, but we're going to for some of the upcoming projects. So just to point out, so like on project 0, 1, and 2, we've been focusing on this tensor, but starting even on project 3, we're now going to be using the autograd functionality in PyTorch and also PyTorch modules. So what are these? Well, autograd is the actual kind of part of PyTorch that implements the computation graph data structure and also the backpropagation algorithm. So all of the code that will automatically compute the gradients for us is going to be within autograd. In addition, a PyTorch module then is going to sort of be like an abstraction for some sort of generic neural network layer. So a module will give us a lot of freedom in defining how our overall architecture is set up, because we can sort of stack these modules together or route the output from one module to another. And in addition, the module will then be responsible for managing the learnable parameters that are specific to that. Right, so we'll have like a module for a 2D convolution and a separate module for maybe a linear layer. And then together with autograd and with tensors then, you get this overall framework set up where sort of the tensors store the data, autograd will compute the gradients for us, and module then will allow us to structure our architectures in like with a lot of freedom. So let's look at an example now of some of these to put this a little bit into kind of like a clear perspective. So what we'll do in looking at some of these examples, so we'll start with tensors, and then we'll look at autograd, and then finally we'll look at modules, and we'll use like a 2-layered neural network as our kind of running example. So what we'll do first is we'll look at how would we implement a 2-layer neural network and even the training of a 2-layer neural network with tensors, and then how would we incorporate autograd, and then finally how would we sort of package it all into a module to try and clean up some of the code. But starting with the tensors, so this is sort of the approach that we've been taking in the projects up to this point, where we're going to do all of the work just by ourselves from scratch with tensors. So in this portion of the code near the top, what we're doing is we're setting up our inputs to the network. So you can see like we're going to have like a batch of inputs X that has like n specific examples within the batch. Each has some dimension of input. We're controlling which device it goes on. We have labels that we're going to be used for training. So we have some final dimension of output for those labels, and then the same number of examples as our inputs. And then we have, because it's a 2-layer neural network, we have 2 learnable parameters, W1 and W2. We're going to be ignoring biases here just for succinctness of the example. But in this first portion of the code, right, this is very similar to what we've been working with up to this point. We're just setting up our tensors for the data for training and also the learnable parameters. At that point then, within the actual training process, you can see like we have this for loop where we're going to be going now over the, I think we're going over the overall, like the entire training set. And what we're doing first is we're computing like the first hidden state as output from the first linear layer. So we have like this, our inputs matrix multiplied with the first layer's weights. We then pass that through a nonlinearity. We then generate a final prediction using the hidden dimension matrix multiplied with the second layer's weights, and then we calculate a loss. So this is a forward pass, right? We're sort of manually going through and performing tensor operations on our inputs and our learnable parameters to produce a final output. At that point then, the way we've been implementing a backward pass or the backpropagation algorithm is in that, well, I think we called it like a flattened implementation, like a flattened approach, where we would, based probably on some paper calculations, decide what the gradients at each intermediate step of our forward pass should correspondingly be. And so once again, these gradients are being computed as just operations on tensors, where we're storing the gradients now into new tensors corresponding to like one gradient for each of the intermediate variables or even the learnable parameters. But once again, we're just operating on the tensors directly. And then at the final step, if we actually want to train this neural network, we can perform gradient descent by updating the values that are stored within our parameter tensors by taking just like a learning rate sized step along the gradient directions that we just calculated. And then because there's a loop, we would kind of continually do this. Right? So this should look really familiar to you from your project 2 implementations. A nice detail, which I think people have been noticing about tensors on PyTorch, is that with this device keyword that's built into the tensor data structure, you can control which hardware device your operations are ultimately going to be computing on by just initializing your data or your learnable parameters on a specific device. So the nice part about this is that this is a very important abstraction that allows us to ignore any of like the difficulties of writing CUDA kernels by merely, as the sort of developer of the architecture, by merely changing what device the data is set up on. Baked into PyTorch, all of these individual tensor operations, like a matrix multiply or a scalar multiply, like where my cursor is, all of those have been built into the low-level internals of PyTorch at a CUDA kernel level to handle cases where the devices are actually on the GPU. They've also been implemented, like those same operations, like the matrix multiplies or the scalar operations, for CPU architectures in C++. But from our standpoint, working in Python, we can ignore how to write a CUDA kernel just by changing which device the actual data is stored on. So this is an important abstraction to think about because it's super easy to kind of take for granted a lot of the optimizations that have been built for us by just working in Python. But just know that like under the hood, there's a lot of complexity going into actually how the operations would be implemented for the specific hardware platforms that you might be working with. Okay, so that's how we would set up like that 2-layer neural network just with tensors. Now let's think about how we could set up that same kind of training process, but now instead of trying to calculate all of those gradients ourselves, we could rely on PyTorch's autograd functionality to do it for us. So the core idea here is PyTorch has interfaced this autograd functionality with the tensor data structure and allowed the developers to control when autograd would sort of be turned on or wanting to track gradients for specific tensors by having a keyword argument for the tensors, which is the requires grad argument. So by default, any tensor that has the required grad like keyword parameter set to true when it's initialized will automatically have the gradients tracked by autograd. So any operations that we perform now on these using these parameter tensors are going to correspondingly have gradients for those 2 tensors tracked by autograd. So what this looks like now is if we wanted to, let's see, so in the next step, so because we're not interested in this example of sort of backpropping or like updating the inputs and the corresponding labels, we don't set requires grad to true for those tensors. But for the parameters of our network which we want to train, we're going to keep the sizes all the same, but just set the requires grad now to be true. At that point then, the rest of the forward pass is still the same. So we've just shortened it a little bit here because, in part because we don't need to keep so many intermediate variables because we're not going to be calculating the gradients. So for our purposes as the developer, instead, we can sort of simplify our forward pass and ignore all of those intermediate variables, even though they still will exist within the computation graph. But just for our purposes, we don't want to manually keep track of a bunch of different intermediate variables. Instead, though, because we have this autograd tracking set up, what we can do is we can request, after we've done a forward pass, for autograd to do the backward pass and actually calculate all the gradients that we wanted it to calculate. So by taking our final output from the forward pass, which is our loss, if we just call .backward on that tensor, that'll trigger AutoGrad to know, like, okay, I need to go and step back through every single portion of the computation graph, and now I'm going to keep track of only the gradients that were requested of me based on the tensors that are being used in those operations of the computation graph. And so if we sort of step through what that is going to do, so during the forward pass, what was happening is, so what we're going to show here on the left is the computation graph as it was being dynamically computed during the forward pass, and then we'll show how backward can use that to update the gradients. So the first step of our forward pass is doing this matrix multiply between our input x and the first layer, right? So here you can see like our input nodes to the graph, and then the one matrix multiply compute node producing some intermediate output, which gets passed to the clamping operation, which is effectively implementing a ReLU, like a nonlinearity. That output then gets matrix multiplied with our second parameter, like our second layer weights W2, and then that gets stored into this variable that we name ypred. So from the standpoint of PyTorch's built-in computation graph, it knows that like these intermediate steps correspond to intermediate variables, but on the Python side, we never gave them names or never like kept track of them. But from the standpoint of the AutoGrad, it does know that there were specific intermediate variables for the purposes of calculating gradients. So at that point then, we were setting up our loss. So we took like an element-wise difference between our predictions and our corresponding labels, which were input. We then did, I think it's like an L2 loss here, like the sum of squared differences. And that produced our final output tensor, which was this loss variable. At that point, what calling backward does is it triggers an actual backward pass through this full computation graph, just like how we talked about with backpropagation. But we, as the developer, we don't have to worry about how any of the gradients are calculated. It's like internally, PyTorch knows how each of these compute nodes in the graph are going to affect the downstream gradients using the upstream gradients, and it abstracts all of that away from us. So we can just worry about our architecture. And after backward finishes, what's going to happen is the graph structure is going to get automatically thrown away, because PyTorch relies on a very kind of dynamic graphs where every time you do a forward pass, it'll keep track of what it needs to in the cache, and when you call backward, it'll do a backward pass, but then kind of throw away the computation graph, in part for efficiency and yeah, I think mostly for efficiency. But at this point of the code, after we've called backward and it's done the backward pass and then it's thrown away the computation graph, all we're left with are our tensors. So we have like our input x, our W1 tensor, our W2 tensor, and our labels y as a tensor. But now there's going to be a .grad property for W1 and W2 based on the result of the backward pass. So this .backward call automatically updates the data that's stored in those two .grad properties for W1 and W2, and that data is itself actually a tensor. So there's actually like an array of numbers which are the gradients for like the loss with respect to W1 and then the gradients for the loss with respect to W2. At that point then, if we were going to use the result of what AutoGrad computed for us to actually perform gradient descent, what we could do is we could update the corresponding parameters. So we could say like W1 is going to be modified by some learning rate sized step along the gradient direction, which was produced by AutoGrad, and then the same thing for W2. The final thing, though, that we have to do here is set the actual gradients now that are stored within these two properties of W1 and W2 to 0, because the way that PyTorch has AutoGrad built in is every time backward is called, it'll do an accumulation operation into these .grad properties. So in other words, every time backward is called, it's going to do like W1.grad plus equals whatever its gradient calculation results in. So in order to ensure that at the next training step, our gradients are correct, we want to zero out whatever was stored from this training step so that we don't kind of keep accumulating gradients from training step to training step. That's just, it's kind of an annoying feature of PyTorch, because actually like that can be a big source of bugs inadvertently if you forget to zero out your gradients during training. One, I guess, nice benefit of it is you can simulate large batch sizes using this. So if you accumulate the gradients across steps and then average them, it's effectively like you used a larger batch size. So in cases like where would that ever come up? Well, it might be the case that you want to re-implement results from a paper that use like a really, really fancy GPU that could have a batch size of like 512 images, and your GPU can only afford maybe a batch size of 4 images. Well, you could simulate that larger batch size by accumulating gradient steps, or like the gradient update across the smaller batches. But it is annoying because it is a source of bugs. The other thing that I want to point out on this is, so in this implementation where we've used AutoGrad, you might be wondering, like, why do we have this code after we've run backward, where we're explicitly like requesting this this like torch.nograd function call? What that's doing is that actually lets PyTorch know that any operations we're going to be performing on tensors within like this portion of the code below shouldn't affect the computation graph anymore. So sort of like ignore any tensor operations we're performing in this portion of the code below the nograd function call for the purposes of updating the computation graph. And conceptually, why we're doing that here is because for stochastic gradient descent, we don't want changes on W1 to affect the next parameter updates on W1, if that makes sense, for the purposes of backpropagation. So we want W1 to get updated by stochastic gradient descent and not have that update itself affect the next gradient calculations when we call backwards at the next training step. So in other words, like this minus equals operation, if we let PyTorch track it, it's going to assume that that should be put into the computation graph and potentially affect the gradients of the next backward pass. But this is a way to ensure that that doesn't happen. Okay, let me pause and see if there's questions on AutoGrad up to this point, or the tensors. What questions can I answer here? Yeah. Yep, exactly. So from the standpoint of PyTorch, any code within this, like below this this torch.nograd function call, is going to ignore tensor operations for the purposes of tracking the computation graph. But outside of that, it's going to track every operation you perform on the tensors for constructing the computation graph. Yeah, I haven't thought about that before. So the question was like, does within this torch.nograd is what's actually happening, is it actually modifying the computation graph, but then once you leave the section, it's like undoing the changes that you made to the computation graph? I don't know. You'd have to look into the PyTorch implementation of that part of the API to see what it's really doing. I sort of doubt it's doing that, but I'm not sure. I've never seen it come up though where like you might want the computation graph from that portion, at least in the context of stochastic gradient descent. So usually when you want nograd, you really don't want it touching the computation graph. Yeah, and I will point out like this, like both like using nograd appropriately, using like zeroing out your gradients, and also setting up which tensors you want tracked, you want the gradients tracked for. Like those three details are the cause of a lot of bugs. So I would say if usually when you use nograd, like you're very explicitly, like you do not want the computation graph to potentially have bugs being like inserted into it. But it is an interesting question that you could look at the PyTorch API for. So yeah, so in this portion of the code, like this is the actual like gradient descent being applied. So what we would be doing here is not like we're wanting to change the weight parameters based on the gradient from the forward pass, but it's like these operations itself, subtracting this gradient tensor from the current weight matrix or weight tensor, that element-wise subtraction is a tensor operation that could actually affect the gradient on W1 if we let it, but not in a way that makes, like, not in a way that that we want it to according to how we define stochastic gradient descent. So like in other words, like if you go back and look at our lecture on like the optimization, we only want to optimize our parameters with respect to the loss. We don't want like extraneous objective terms added in. We just want our like the data loss and the regularization loss that we talked about. Well, in this case, the batch size actually isn't equal to 1, right? Like the batch size here is actually like all of our images. So it's this n, which in this case we say is 64. So this gradient that we're calculating according to this loss, like we're not actually dividing by the batch size. That is a good point. What you might want to instead do is say like have an additional line here that says like loss is equal to loss divided by the batch size, which is effectively like scaling your learning rate. So your learning rate kind of could potentially account for that, but yeah. Okay, so yeah, one of the thing to think about on that question is like, so because we have this summing operation, within the gradient calculation, we're going to accumulate all the gradients across the batches into the parameter vector. Yeah. Okay, good question. Okay, so that's how we could implement training with tensors, but also with AutoGrad instead of having to manually compute the gradients. Another thing that comes up then is this question of actually like what functionality from the standpoint of actual operations can we use? Like could we maybe define our own functions and have this AutoGrad functionality still work? And the answer there generally is yes. So if you set up a Python function that uses like internal tensor operations that PyTorch is compatible with, so things like element-wise addition or the sum operation, or a lot of those ones that you're now familiar with, you can actually encode those into some Python function, like what's shown here as like this sigmoid function, and then call that sigmoid function and give it input, which is a tensor, and AutoGrad will still know, or will still be able to sort of use that function within the computation graph for backprop. So you can see here, like we're calling sigmoid now on the output from R2, or at least from our first layer. And so what the actual computation graph now is going to look like is it's going to essentially, PyTorch will be able to kind of like go into this function and know what each of these operations we were requesting within the sigmoid function, and correspondingly represent those in the computation graph for the purposes of the backward paths. And the reason why this will sometimes come up in practice is you might want to maybe like define some new loss function, or maybe define some new activation function, and you can derive on paper like an optimized implementation for it. So in the case of sigmoid, for example, we saw how for the purposes of backpropagation, it had like a very nice kind of concise representation for how we could calculate the actual downstream gradients. And that nice concise version was more efficient than doing like a naive backward pass through each of the individual like sub operations within sigmoid. So what you could do for efficiency is you could instead choose to actually define the specific AutoGrad operators for this new function that you're giving it, instead of relying on the default AutoGrad. So this would sort of be like a more advanced step. This is more, you would only use this in the case where you want to have some extra optimization on the new functions that you're using, instead of just what's built into AutoGrad. But if you wanted to do that, what you could do is you could inherit, or you could sort of subclass now a sigmoid class, which inherits from this AutoGrad function, and then you could specifically implement the forward pass and the backward pass, where you're storing in essentially the cache, which is PyTorch calls it context. So you're storing into the cache what variables you need for the backward pass here, and then you could implement your sort of optimized backward pass. So in practice, you would really only do this extra optimization if you specifically wanted to do exactly that, like optimize your code beyond what AutoGrad will do for you. But in general, just the built-in AutoGrad backward pass is usually going to be enough for most of your implementations. The other thing that's worth pointing out is if you do decide to implement your own AutoGrad function, so this subclass, the actual computational graph that PyTorch is going to use during AutoGrad will be different. So if you just implement sigmoid using like these naive or like these built-in operations like division and addition and the exp function, the computational graph is correspondingly going to represent every one of those individual operations as compute nodes within the computational graph. Instead, if you define an explicit subclass of the AutoGrad function, there will just be one node in the computational graph to describe that AutoGrad function. So another way to say that is there's essentially an AutoGrad function built in for like element-wise addition, element-wise division, the exponential function, and that's why you have nodes within the computational graph on the left-hand side. Okay. Yeah, but in practice, doing this extra optimization is pretty rare. Usually all of the functionality that PyTorch has built in terms of these built-in operators is usually enough, certainly to set up your CNN or your neural network. But then it's just a question of if you want to optimize it, you could potentially move to this. Okay, so one useful package within PyTorch is there's a neural network package called NN, and it has a set of kind of nice utilities that you'll commonly use. So, and this will help kind of simplify a lot of your code. So, for example, one thing that's very common is you might want to have like a sequential neural network that just chains together layers. So torch.nn implements exactly that for you. So within this higher level API, like this is just one example of the type of functionality that's built into this package. So what you can do is you can set up this torch.nn.sequential object and then pass it the specific layers that you would want. And it will then correspondingly treat that as an overall basically like PyTorch module, which we'll talk about coming up. And it'll be able to keep track of during the forward pass, I'm going to pass input to this model to the first linear layer, and then the output from that first linear layer is going to go to the ReLU layer, and then the output from the ReLU layer will go to the next linear layer. So it'll automatically do the forward propagation of inputs to outputs for you. And also because it's all built within, like compatible with AutoGrad, it'll know, like AutoGrad will know how to backward pass through these. In addition, one thing you're probably noticing is like we have now this nn.linear layer. So also built into this package is a set of very common layers. So you have like activation functions like ReLU, you have linear layers, you have convolutional layers. And the nice thing about them is they will track automatically for you the learnable parameters. So all you'll have to do for setting up one of these layers is specify some of the hyperparameters. So you'll have to specify like the input size, the output size, maybe the kernel size in the case of a 2D convolution. But then internally within this within an instance of this linear class, it will track what the parameter tensor needs to be. So it'll do the initialization for you, and for the purposes of making sure that like requires grad is set to true, it'll know to do that for the trainable parameters. And if there happens to be some layer that has non-trainable parameters, it'll know to set the requires grad to false for those layers. So that's a nice bit of functionality built in. So now you can see, for example, like with this sequential layer or this sequential model that we've defined, we could simplify our code quite a bit by just passing the input directly into it, and it'll go through all of the individual layers for us during the forward pass. Mm-hmm. Yeah, so the question was like for this linear layer as an example, can you control whether you have a bias set? Yeah, so by default in PyTorch, it will assume that you want a bias, but there's a keyword argument that you can pass to this initializer that can control whether there's a bias set. There's also keyword arguments that can control like which initializer is used for the initializing of the learnable parameters. And depending on which layer you're looking at, so like a linear layer will have different keyword arguments than a convolutional layer. And so those keyword arguments are always going to correspond to the hyperparameters for that type of layer. So the question was, what happens when AutoGrad runs into a function that it doesn't know how to differentiate? You'll get a runtime error. So you'll get a runtime error. And the exact, I don't remember exactly what that will be called, but you'll get some PyTorch built-in runtime error. Yeah. I would say you have to be trying pretty hard to have the forward pass work and the backward pass kind of not work with PyTorch. Like there's a lot of operations built into PyTorch. So if your forward pass is working and your backward pass somehow is failing, like that's I would be interested to see what function can cause that. Yeah. Okay. So this NN package within PyTorch is going to simplify our code. It also has loss functions built in. So here you can see we're calling like this mean squared error loss function, which again is going to simplify those calculations that we had in the preceding example. But our loss.backward is still going to stay the same. So because this is all integrated with AutoGrad, it still knows exactly which parameters within each of these two linear layers are trainable, so which it should be tracking gradients for, and it will all work very seamlessly. The thing, though, that we need to change now that we have this model set up, instead of doing the actual two layers ourselves, is for the purposes of training, what we have to do now is we can request from this model object the specific parameters, and it'll know which of them are trainable. So at this point, like, we can iterate through which of the trainable parameters exist within the model, and then apply the gradient descent update to each of them. And once again, though, we still have like our zero grad operation. Just now we're applying it to the overall model, and the model, this sequential class, knows that there's a member function called zero grad, and it knows how to apply that to the specific learnable weights, just how we did when we were implementing it, the zero operation ourselves on the W1 and W2 from the preceding slides. Okay, another utility function is it's actually kind of a pain to implement that gradient descent update ourselves. And for the purposes of maybe like those more complex optimizers like Atom or RMS prop, it'll be like really a pain to maybe have to define those different updates for different like architectures. So instead, what's built into PyTorch, which makes it really easy, is there's an Optim package in PyTorch which supports the very common optimizers for us. So here, for example, you can see what we do is we set up optimizer as an object, which is of type, or it's an instance of the class Atom, and we give this as input the parameters that we want this optimizer to be optimizing. And then there's going to be some hyperparameters for each of these different optimizers, like we talked about. So like with Atom, there's a learning rate. There's a few others, which we're just going to use the default parameters because we're not passing them as keyword arguments. And this optimizer now will know to actually update only these parameters that we passed. So within the actual training routine, now instead of having to iterate over each of the parameters and apply our gradient step, now what we can do is just request, after we've done a forward pass and a backward pass, we can request that the optimizer takes a step. And so internally now, the optimizer knows which parameters it should be updating, and because we called backward still, those gradients for all of those parameters are going to be calculated by this point that we're calling the step. And now we can zero out the gradients by calling optimizer.zeroGrad. You could also call model.zeroGrad, but they're both going to do the same thing. And so you can see like what's happening as we're kind of going through these different, as we're kind of progressing, our code is getting seemingly simpler and simpler at the highest level, right? Like at the highest level, we're using less and less code, but we're actually performing the same operations. So we're still training a two-layer neural network with the same input and output size and hidden layer size. But for the high-level developer, it's becoming kind of easier to set this up. We don't have to worry about so many of these low-level details. So this can be really nice if you're focusing on your architecture and you don't want to have to worry about the details of the optimizer. You just want to take an off-the-shelf optimizer. PyTorch will abstract away a lot of the complexity that goes into implementing that optimizer. Okay, so we saw like that sequential model, and we sort of were mentioning that is a module within PyTorch. So the module was the third core concept that we said existed within PyTorch to help our development. So there was the tensor, there was AutoGrad, and then finally there was this module idea, which is what we can use to represent individual layers or individual networks. So a PyTorch module, it is a this abstract class representing a neural network layer. So its inputs are always going to be assumed to be tensors, or Python variables it can also take as input, and the outputs are going to be tensors or Python variables. And so the way that you'll set up let's see what else. So modules, they can also contain weights. They can also contain other modules as member variables. So if you wanted to represent an entire architecture as a module, you can have other modules that are member variables of your architecture, which are themselves individual layers, which is what we're doing here. So you can see, in this case, we have this class 2-layer net, which is a subclass of the torch.nn.module class. And within its initialization routine, you can see it's setting up 2 other modules, these 2 linear modules, as member variables. So now this overall 2-layer net class is representing our overall architecture, and it contains individual layers within it. So within setting up one of these modules, what you'll have to do is define an initialization function for it. So that's where you should set up any member variables, any parameters that you might want it to be learning, or like these layers within this case. And then also a forward function will be needed to describe how your model should transform the inputs into the outputs. And so, yeah, so the initializer, it's, in this case, it's setting up these 2 children. One thing you'll have to do is this like super initialization, which runs the initializer essentially for the parent class, which in this case is the torch.nn module. That's just kind of like an implementation detail, but I'll just point out, like, every time you see a subclass built with PyTorch, a subclass of this neural network module, you'll always see this super initialization. Generally, in some complex implementations, you might see like passing specific values to it, but as keyword arguments or arguments. But for starting out, you can ignore it. But you'll always include, though, I'll just point out, you'll always include this line because that will initialize the parent class. And so, yeah, so we set up the initializer, we define a forward pass to describe how the inputs are transformed to outputs, and we don't have to define a backward pass because it's now a subclass of this neural network module. It'll be integrated with AutoGrad automatically, and the backward pass we'll leave to AutoGrad to figure out how to calculate. And so, yeah, so it's very common, let's see, to mix and max custom module subclasses within a sequential container. So that's a nice part of, like another nice part of using like this neural network module structure is you can integrate it with other like utility functions or other utility classes built into the neural network package. So you can see like we're defining our own module up here, this parallel block, and then we're incorporating that parallel block within a sequential, within one of these sequential containers. And again, like the only reason we can do that is because like this PyTorch API is well defined and it's internally consistent. So like the sequential container knows that there will be a forward function implemented for each of the parallel blocks that we were giving the sequential container. Define network component. Yeah. So what this code then is doing, we could think about it is it's like this is now what will make, for example, implementing some of those CNN architectures we talked about, like ResNet or GoogleNet, which had those repeating block structures, very easy. Because what we can do is we can just define this like relatively abstract class of a parallel block and then stack multiple instances of them together within our sequential container, which in effect, if we were to think about what the computational graph would look like, it's going to be stacking together multiple of those blocks. And because this is all using AutoGrad, we don't have to worry about this really complex backward pass to calculate through like these many blocks. It'll just automatically get implemented for us. Okay. So another really important class within PyTorch to think about, there's actually 2 that are related. One is a dataset class. Another is a data loader class. So obviously, this is a data-driven approach, right? All of neural networks are data-driven approaches. So how it is we interface data with these deep learning frameworks is an important topic. And so what PyTorch does to support that interface is there's a generic dataset class. So here you can see we're describing this tensor dataset instance. So it's an instance of the tensor dataset class, which has example inputs X and then example labels Y. But that then is itself, that dataset instance is passed to a dataset loader instance with a corresponding batch size. So what these 2 PyTorch classes do is they work in tandem. So a PyTorch data set will be responsible for actually loading data from disk into some Python tensors. And then the data loader is what will be responsible for batching samples from that data set for actual use during training. So if you have some, in this case, like our entire data set is just loaded into memory initially, but generally what's more common, like if you're working with like an image classification data set, is you won't be able to load the entire data set into memory. So if you're working with ImageNet, you probably won't have enough RAM on your CPU to actually load all of ImageNet into memory. So instead what you'll do is you'll implement some data set class, which will, for a specific, like once the data loader requests a specific image, like image with an ID of 0, then the dataset class will be responsible for actually going to disk and actually loading in, let's say, some JPEG file, and then storing it into a Python or PyTorch tensor, and then giving that tensor back to the data loader to decide how it should put it into a batch. So once we've set up a data set and then correspondingly a data loader for that data set, what we can do, which is really nice, is during training, we can actually treat the data loader as an iterable. So we can do a for loop over that iterable data loader, where it'll automatically sort of batch the data for us. So if you want to implement your own data loader to do batching in some custom way, you can do that. But the default data loaders within PyTorch generally are pretty useful for actually doing random sampling for your batches. And for most use cases can work kind of out of the box. So once again, like our code is kind of getting simpler in a way, like our training code now. We don't have to manually go over the specific number of images within our data set or like handle knowledge of that. We can kind of like leave it to the data loader to handle. Okay, another thing to point out about PyTorch, which is really nice, is there's kind of a separate extension to PyTorch called Torch Vision, which is its own Python package, and it has pre-trained models available that will download from like some online database where they store the actual model weights, and also the architecture is set up for you. So for like VGG, for ResNets, for AlexNet, for a lot of the common image processing networks, there are these models that have already been pre-trained on ImageNet and you can use right out of the box. This is also really useful for if you want to take maybe a model trained on ImageNet and then fine-tune it on one of your own tasks. You can use the built-in implementations and the built-in pre-trained parameters from PyTorch to ease that development for you. So if you're curious about that, the documentation is linked on this slide. Okay, so we mentioned earlier this notion of PyTorch using dynamic computation graphs, and I think now what I want to do is just kind of like go through an example of how that is sort of useful. So in this portion of the code, it's still in this case, so it's still our 2-layer linear neural network. And so during the forward pass, like we were talking about, what happens is internally, PyTorch is going to be building this graph data structure. Somewhere within PyTorch, it's storing the knowledge that it needs to represent this graph data structure. And at the same time, it's also computing the actual operations to generate the output. And then once we have our final output for some training objective, like a loss, we can then call backward to go back through this computation graph and actually update the gradients within all of the parameter vectors. At that point in the code, right, what we were mentioning is that once it's gone through that backward pass, the whole computation graph gets thrown away. And at the next training step, it goes and redoes all of that construction of the computation graph once again, so that we could then once again call backward potentially to actually update the gradients again. And so all of this process is what's referred to, like this process of constructing the graph and then throwing it away for every time there's some forward operations and then a backward call, is what is referred to as like this dynamic computation graph within PyTorch. Because essentially for every forward and every backward, you're dynamically constructing and then dynamically throwing away the graph. Okay, so once again, so this dynamic computation graph, it's just this idea that every time you do a forward pass, PyTorch will store information that it needs to construct the graph, and then when you call backward, it'll actually construct the graph in memory. But once backward is done, it throws that graph away. And so it's worth thinking about why this is potentially useful, right? Because it seems, at least in this kind of somewhat simple case of like of this training cycle, it seems a little bit wasteful to keep reconstructing and then throwing away your graph. The reason that this is useful is that it gives you a lot of control at the highest level for deciding essentially what you want your program to do in terms of control flow. So what you can do is, like, every iteration maybe of training, you could have some if statement that decides which computation graph you set up based on the actual input data. And I know that seems like a weird example, and sometimes it's kind of hard to come up with examples of control flow that make sense, but there are certain network architectures you'll see where maybe you want to actually decide which branches you take in your network based on like some intermediate output from the architecture. And so you can implement that very easily in Python, and then the computation graph will get dynamically computed every time you run the forward pass. So this computation graph will be dynamically constructed, depending on which specific branches you're following for your implementation. Once again, I know it sounds kind of strange to think about, but you'll actually find in practice that notion of adding control flow in the case of like if statements or while loops or for loops within your network architectures is actually somewhat common. I think you're referring to, in the case of GoogleNet, how they had classification heads baked into like intermediate, so they had like a final classification head at the very output of the network, but then they also had like those intermediate classification heads. That's a little bit different because in those cases, they would still, what that was doing is trying to give like additional training signal to those earlier layers. And they would still, I think, classify and generate like a portion of the loss from each one of those intermediate layers. But it might be the case that, and I know this sounds weird, but it might be the case that maybe you want to have, like maybe you want your model to specialize between like above water image classification and below water image classification. But your data set is all mixed up maybe. And so you have an if statement in your model that says, if I get a batch of data from my above water camera, I want it to run one portion of the network. But if I get a batch of data from my below camera, I want it to run a different portion of the network. And this is what the dynamic graph allows you to set up very easily in PyTorch. And so, yeah, I'm going to kind of, for the sake of time, I'm going to move a little bit faster. So this is so this notion of a dynamic graph is in stark contrast to what you might think of as like a more like what you might have thought is happening with the computation graph, which is that it gets set up as a static graph. And so that is like you would set up your architecture, and then you would assume that the architecture never changes. So for the purposes of backpropagation, you should assume that your computation graph doesn't change ever. And that would be a static graph. And this can be implemented with PyTorch. So there's a concept from compilation called just-in-time compiling, which is where you would run a compiler to just in time. So programming languages like Julia, for example, have a nice scripting style similar to Python, but they have nice efficiency similar to C++ because they use a just-in-time compiler, which is in contrast to Python, which is itself an interpreted language, so it doesn't have just-in-time compiling. But side note, but PyTorch does have there is just-in-time compiling with PyTorch. So what you could do, if you know that your graph is never going to have like control flow that will potentially affect the backpropagation during training, you could request a static computation graph with PyTorch using some of this just-in-time compiling API, but this is something that you won't do right out of the box. So I'm not going to spend too much time talking about this. This is the actual function call here that requests the computation graph get compiled. The reason, though, I do want to point out about why static graphs are sometimes useful in contrast to dynamic graphs is, and this should be familiar for anyone who's taken like a compiler class, it should be pretty obvious that if you have a static data structure or a static program, you can represent a lot of assumptions baked into like your IR within your compiler and basically make a lot of optimizations. So the more static a program is, the more assumptions your compiler can bake in for the purposes of optimization. Whereas the more dynamic your program is and the more that its control flow depends on the input data, the less optimizations you'll be able to run. So the same goes for the case of computation graphs. If you have a static computation graph, it'll tend to run faster, and that's kind of what the PyTorch 2.0 is moving towards, is trying to help add more optimizations. But you lose some flexibility in deciding what the control flow of your program is or your computational graph based on your inputs. So that's mostly the trade-off. Yeah, so static, the idea is once the graph is built, it'll never change. But dynamic, on the other hand, is this idea that the computation graph can sort of change at every iteration, depending on what the control flow of the program says it should do. And so a few cases where like dynamic graphs that are inherent in PyTorch are nice is so like recurrent neural networks and kind of a similar idea of like recursive neural networks tend to have very like dynamic graphs, because you might have like different windows of inputs for different batch elements, and so the length of your dynamic graph in that case can change from input to input. So like the particle filter networks, which we'll talk about later on, would be an example of a recurrent network, which is where dynamic graphs have a nice use case. Also, if you have like modular networks, so there was a similar, so this paper is also linked on the website, of like composing neural networks for both perception and planning within a robot. This is another case where like if you may be like adding different networks throughout the course of your robot's operating, you would maybe want a dynamic graph. And then also for your final project, you'll be using the dynamic graph implementation of PyTorch. So we're almost out of time, and that's kind of exactly where I wanted to get to. I'll just briefly point out, I just want to contrast briefly. So these slides are up online, but I just want to contrast PyTorch versus TensorFlow. So on this idea of like a static graph versus a dynamic graph, one of the big distinctions between PyTorch and TensorFlow early on, so in particular like TensorFlow 1.0, is that TensorFlow 1.0 was static graphs by default, while PyTorch was dynamic graphs by default. That contrast, I think, led to a lot of interest in PyTorch. And so since then, TensorFlow has moved towards becoming more dynamic by default and trying to provide some high-level APIs similar to PyTorch using what's called Keras. So there's a Keras high-level API. So the two, though, are generally moving towards each other. So I think increasingly, like, there's not a huge difference between the two, but sometimes historically you would see arguments about why the PyTorch dynamic graph structure is beneficial for certain types of network architectures. So with that, that's everything for today. Next time, we'll talk about object detectors. And thanks for coming out. I'll see you tomorrow, too, for discussion.